Hi everybody, we're talking about lesson number 4, electronic structures. Now the big idea here is that electronic structure of an atom is based on the orbitals associated with each atom. So when we're talking about electronic structure, we're really talking about its electrons. So remember Bohr models back in grade 8, 9, and 10 shows that electrons are arranged in orbitals. And you might remember this model. This model is called the Bohr model. And that electrons cannot occupy between the orbits. Cannot be between the orbits. Now, also with Bohr models, we also know that atoms want to gain what we call noble gas stability. Now what you might know this is called the octet rule, which you might remember means the full valence shell. Where the outermost shell is called the valence shell and the outermost electrons are called the valence electrons. So thus, how do they gain or lose? Gain or lose electrons? Or how do atoms do that? They want to gain or lose electrons to become full. So let's start off with drawing Bohr models. How do we draw Bohr models? Well, the first thing we want to remember is find number of electrons. You need to know the number of electrons this atom has, for example. Number 2, remember each shell fills max is 2, 8, 8, 18, and so forth. Okay. The third thing is fill first 4 electrons unpaired. Now what that means is you want to fill the first 4 electrons in a north, east, southwest pattern before they pair. And it comes into what we call how electrons are the same charge and they don't want to be near each other until they have to. Okay? So let's take a look at these examples. Let's draw the Bohr model of the following. We have lithium. Now looking at the periodic table, we see that lithium has 3 electrons. So where do the first electrons go? Well, the first 2 can go in the first shell. Now the first shell is maxed out. Where does the last electron go? It goes in the second shell. Oxygen has 8 electrons. So the first 2 again goes in the first shell. Now there's 6 more to go, so it goes north, east, south, west. That's 6 of them. 7 and 8. Now note how these electrons are filling in only these regions, and that will come to play when we continue on this rest of this lesson, why they fill in that order. Lastly, carbon. Carbon has 6 electrons. So again, you go first 2 goes in the first shell, the next 4 goes here. So they do not pair up yet. Now if you need a little reminder, you would see that in this next page right here, this is a table showing you what will happen based on the group number. Okay? The different groups of the periodic table will do the following. So why do elements want to gain or lose electrons anyways? Well, first of all, the biggest thing is every element wants electrons. They need it. And we call that affinity. Affinity means attraction. Just that some have a higher affinity. And you might know these ones are your nonmetals. And we can measure affinity. We call this electronegativity. And that will come into play when we go into a lesson on periodic trends. The higher electronegativity, the more it wants to gain electrons. So which one do that? The nonmetals do that. Alright? So let's go into the Bohr model of this element right here. So we have lithium chloride. What do we get? Well, when we look at lithium chloride, well, we drew lithium earlier. Lithium looks like this. Chlorine has 17 electrons. So lithium only has 3. So the first 2 goes in the first shell. The next 8 goes in the second shell. And that's 10 right there once I finish drawing the second shell. The third shell has 7. So 1, 2, 3, 4, 5, 6, 7. Okay, so look at this example here. What will happen? Well, what will happen is that these 2 elements want a full outer shell. And because they want a full outer shell, they will have to either gain electrons or give up electrons. Lithium here could either give up this one little electron or it could gain 7 more. Chlorine can either gain 1 more or it could lose all 7. Which one would they rather do? You could think of it as the path of least resistance. So the elements want to have to do the least amount of work in terms of losing or gaining electrons. So lithium will want to lose an electron. Chlorine will want to gain an electron. So lithium goes, I want to get rid of this electron. Chlorine goes, I'll take it. And this is how ions are formed. Where all of a sudden you have lithium and chlorine forming a compound called lithium chloride. And this is what you're going to get. So chlorine will look like this now. And once you finish drawing chlorine, you're going to notice that chlorine now has a full outer shell. Lithium also has a full outer shell. But what do we have to do next? Well, in this case, because they're no longer balanced charged, they're now charged, we got to put brackets around them and show that they are charged. Where lithium has a +1 charge. We put it outside with a bracket. And chlorine has a -1 charge because it gained an electron. Notice how the charges are still, if you add them up, will still be 0 because it's still neutral. So what this shows you is that electrons can exist in specific orbitals and they can move around between different elements. So wait, how does Bohr model relate to electronic structure then? Well, what it does show you is that electrons occupy orbitals. But one thing that Niels Bohr found was that electrons can jump between orbitals. So yes, they could actually go from a lower orbital to a higher orbital, where each orbital has what we call a different energy level. And because it has a different energy level, it takes more energy for it to go farther away from the nucleus. But here's the thing though, when these electrons are at the higher energy level, they don't want to be there. So they will drop back down. When they drop back down, they will release energy in the form of light. So electrons, when electrons go up to a higher orbital and return to its ground state, you could call it, it releases light. And that is what Niels Bohr found when he dealt with, for example, hydrogen. What he knows is that hydrogen only has 1 electron. So if you draw this 1 electron right here, okay, if that 1 electron was to, for example, go from this orbital to the next one, and when it drops back down, it will release this red light spectrum here. If this 1 electron goes up and jumps by 2 and goes back down, it releases this green one. And lastly, if it goes up 3, for example, it will release this blue one. And that's what Niels Bohr saw. This is called a spectrum, the line spectrum of hydrogen. Now you could see this in a demo we call the metal ion flame test. If you Google metal ion flame test, you'll see that different elements will do this and produce different colors because of the amount of electrons that are jumping. Now, what are some terms we need to know to progress into the rest of this lesson? Well, one of the key things is we're not going to now get out of this Bohr model system of looking at atoms. We're going to enter another form of ways we look at atoms. Now, this may look confusing when we jump into it, but what you need to know is that is what we call that we don't have to memorize what they look like, but we have to know that they do exist. Okay, so the first thing we need to know is what we call an energy level. An energy level is the amount of energy in an electron has. The second term, orbital. Orbital is the region of space occupied by an electron in a given energy level. Okay, but this is where it changes a bit. Shell. Shell are a set of orbitals with the same energy level, and we call this, there's an n value. It's a specific number, for example. And the last term is called subshell. A subshell is a set of oh, there we go. What is going on? Okay. Is a set of orbitals that look the same. So let's take a look. Alright. Now I apologize that this disappeared. There's just something glitchy with my OneNote. Hopefully it will come back soon. So, if you look at this here, all of these are what we call electron clouds. These electron clouds are basically regions of space in which an electron can exist. So electrons don't just orbit around a nucleus like a planet. Instead, it moves around in a cloud. Imagine this edge of the cloud is like a fence, and these electrons could be in that region of space. Now, orbitals are the region of space in which an electron occupies. These are all orbitals. Each one of these orbitals have what we call the same energy level. How do we know that? Because they're all in the energy level 2. The last thing we got to talk about is shell. A shell is a set of all orbitals that have the same energy level. They're all energy level 2. Subshell is a set of orbitals that have the same look. So in this case, subshell, they look the same. So we have a subshell here called S. We have a subshell here called the P's. So they look the same. Well, shell just means they're in the same energy level. Okay. So what are the different types of subshells? That means they look the same. Are all these orbitals the same? Are they different? Well, first of all, we got to talk about different types of subshells. There are actually 4 types of subshells. The first one is called the S type, where we have what we call one s orbital. Now here's a key thing though. Each orbital contains still 2 electrons. Okay? And S-type contains 1 s orbital, we call it. There's also what we call P-type. P-types contains 3 p orbitals. which then, because each orbital contains 2 electrons, this is 6 electrons. We also have D-type. D-type contains 5 d orbitals, which will contain 10 electrons. And lastly, we have F-type. F-type contains 7 f orbitals, and this is 14 electrons. Okay, so let's bear with me for a second. So we have s orbitals, p orbitals, d orbitals, and f orbitals. Each one is a subshell. That means s orbitals will look different from p orbitals, which will look different from d orbitals, which will look different from f orbitals. And that means that each of these orbitals contain electrons. So let's take a look at the first one. S orbitals are round. That means in this one s orbital, there are 2 electrons inside of it, somewhere in this region of space. This 2s orbital, there's also 2 electrons inside of it, in some region of space. Now what a node is, a node just means that the electrons cannot exist around this solid line around. So that means when they were to go from this region to this region, they actually, in a sense, you can think of them teleporting because they can't go through the node. Okay, so these are s orbitals. So there's one s orbital per each energy level, per each shell. Next one. These are p orbitals. That means, again, there's 2 electrons in this one. There's 2 electrons in this one. And there's 2 electrons in this one. So that's why there's 6 electrons total. These p orbitals look like this because they all look the same, just their orientation changes based on how you look. So that's why this is called 2px, because it's on the x-axis, 2py, and 2pz. Alright, notice how s orbitals and p orbitals look different. Alright, so what we also need to know is 1s and 2s, these 2 orbitals, they are on different energy levels. So that means this 2s atomic orbital and these 2 p orbitals are in the same shell. Okay, so these are in the same shell. So if I were to draw a circle around them, if I say that these right here, this right here, is in one shell, and this one right here is in another shell, you might start noticing a pattern. 2 electrons in the first shell, 2, 4, 6, 8 electrons in the second shell. That is actually the Bohr model still, in terms of how many electrons we have. The next 2 look a lot more complicated. Again, we don't need to know how to draw these orbitals. We just need to know that they exist. This is called the d orbitals. D orbitals, there are 2 electrons in here that somehow orbit in this cloud, 2 electrons in here, and so forth. Each one of them has 2 electrons. So that means if you look at it, the total here is equal to 10 electrons. And lastly, these are called f orbitals, where each one has 2 electrons, so we have a total of 14 electrons. So if you look at these, you go, does that mean atoms look like this? They're not spherical? No, it's not. Because if you add up all these orbitals together in the sense that they overlap, because really still, in the middle of each of these orbitals, in the middle, say for example right here, there's still a nucleus. So that means if you add up all these orbitals, they still form a spherical shape. So atoms are still spherical because you add up all the orbitals because they overlap. So if you look at this, how do electrons occupy each orbital? Well, the first thing is they always fill lowest energy level first. What that means is it always fills from energy. If n is equal to 1, it will fill this first. So it will always go in this order. N is equal to 1, n is equal to 2. So these are just energy levels. 3 and so forth. Second thing is 2 electrons fit in each orbital. Now if you flip to page 153 of your periodic table, you're going to see what we call an orbital energy diagram. An orbital energy diagram just shows you the fill order of these electrons. So if I pull up an example of this one right here, you will see that 1s, so if energy increases going this way, you're going to have 1s being the lowest energy level because it is the one that is least energetic, and thus you could put 2 electrons in this 1s orbital. Then you have 2s, so 2 more electrons go here, then 2p, then 3s, 3p, and so forth. This might look really confusing right now, but this scale is actually really helpful when you start filling electrons because it allows you to see where you fill up first. You always know you always go up in order from lowest energy first. Another easier way to actually remember it is just actually these orbitals relate to the periodic table, in which if you look at this, you see that all the s orbitals are where the alkali and the alkaline earth and the hydrogen and helium are. Where all the d orbitals are where the transition metals are located. The p orbitals are where all the non-metals are located, and the f orbitals are where the actinides and lanthanides are located. So how do you read this? Well, let's do an example. Let's say we're talking about a certain element such as, let's say, where is gold? I believe gold, let me pull up our actual periodic table. Gold is located here. Okay, so second to last one on the d orbital. Okay, so here is gold. It's AU. Now looking at where gold is AU, what orbitals will gold have? Well, first of all, gold, if you look at this, has 79 electrons total because it has atomic number 79. What that means is 2 electrons will fit in the 1s because it'll fill out the 1s first. So how you read this is that you always look at where the element is and you go backwards to see what electrons they have. So you look at this, gold has 9, because it doesn't have this last one, it has 9 5d electrons. It has 2 6s electrons. It has 6 5p, 10 4d, 2 5s, 6 4p electrons, 10 3d, and so forth until you get back to hydrogen. Likewise, if you talk about, for example, iron. Iron is number 26. So iron's right about here. This is iron right here. Iron will only have, in this case, 6 3d electrons because it has 26 electrons total. So 6 3d, 2 4s electrons, 6 3p electrons, 2 3s, 6 2p electrons, 2 2s electrons, and in this case the last one is it has 2 1s. Where hydrogen right here only has 1s electron. So that is how you use this periodic table to help you guide you. Now our next lesson, we're going to learn and write out what electrons each of these elements has, and that's called electron configuration. But make sure you keep yourself safe and healthy, and I'll see you soon.